Hello friends, I am Dr. Manisha Verma, teaching physics in Delhi University since last 30 years. Today I will be discussing a very important topic in thermal physics, which is the heat engines. Before beginning with the mathematical calculations involved in the heat engine, let me first introduce you what is a heat engine. A heat engine is a machine that can convert heat into work. To be a useful device, it has to operate continuously. That is, it has to operate in a cycle. At various stages of the cycle, the system may be gaining heat from the surroundings or losing heat to the surroundings. That is, we may be doing work on the system by compressing it, or the system may be expanding and doing external work. This figure is showing the schematic of a heat engine. A heat engine has to operate between two reservoirs, a hot reservoir and a cold reservoir. A hot reservoir is maintained at temperature T1 and it is called the source. The cold reservoir is maintained at temperature T2 and is called the sink. What the heat engine does is that it absorbs heat Q1 from the source and rejects heat Q2 to the sink. In doing so, it does some work which is equal to the difference between the heat absorbed and the heat rejected. One very important thing is this, that the thermal capacity of the source and sink has to be infinite. That is, even though the source is taking in heat from the source, the heat engine is taking heat from the source, its temperature should not decrease. The temperature T1 and T2 remains a constant. Every machine has an efficiency of some kind to find out whether that machine is working properly or not. So, the efficiency of a heat engine is defined as follows. All heat engines absorb heat from a source at high temperature, perform some mechanical work, and discard heat at a lower temperature. The efficiency of a heat engine is denoted by eta, a Greek symbol, and it is defined as the ratio of the net external work done by the engine during one cycle to the heat supplied to the engine during a cycle. If a heat engine absorbs Q1 amount of heat from the source and rejects or dissipates Q2 amount of the heat to the sink, that is, it is the heat rejected, then by the definition of efficiency, eta is given by Q1 minus Q2 over Q1, which is equal to 1 minus Q2 over Q1. Because it is 1 minus Q2 by Q1, this means that eta is always less than 1. Eta equals to 1 means 100% efficiency, and it is not possible to construct a heat engine which has a 100% efficiency. What is the physical significance of 100% efficiency? It means the heat engine is absorbing heat Q1 from the source and converting the whole amount of heat to work, which is not possible. It has to reject heat to the sink. The material used in the operation of an engine is called the working substance. For a steam engine, this is water vapor. For a Carnot cycle, the working substance is the ideal gas. Since the process is cyclic, it means the internal energy at the beginning of the cycle has to be equal to the internal energy at the end of the cycle. That is, U1 has to be equal to U2. From the first law of thermodynamics, we therefore have U2 minus U1 is equal to 0 is equal to Q minus W. So, Q is equal to W, which means that the net heat flowing into the engine equals the net work done by the engine. This is a very, very important result because heat engine is operating in a cyclic manner. Now, depending upon the nature of various processes during the cycle may carry various names such as Carnot cycle, Stirling cycle, Otto cycle. every cycle has different processes occurring in it, though in a cyclic manner. So depending upon the process, whether it is isothermal, whether it is adiabatic, whether it is isochoric, the cycles have different names. So here we will be concentrating first of all on Carnot cycle, because this is the most important cycle. It is probably the best known reversible cycle, Carnot cycle. It was first proposed in 1824 by the French engineer Sadi Carnot. This cycle is an ideal cycle. This is a very, very important point. It is an ideal cycle. It cannot be realized in practice. It is impossible to construct a Carnot cycle in practice. All losses due to conduction, radiation or friction are absent in this cycle. Therefore, it is impossible to construct it. All expansions and compressions, processes which take place in the Carnot cycle, are considered quasi-static. By quasi-static we mean it is occurring so all the processes are proceeding so slowly that they are almost stationary, quasi-static. Again I reiterate, it cannot be realized in practice. And one more thing, the working substance in the Carnot cycle is the ideal gas. The Carnot cycle is the most efficient power cycle, and it is composed of 4 totally reversible processes, 2 isothermal processes and 2 adiabatic processes. This, the hypothetical heat engine that operates on the reversible Carnot cycle is called the Carnot heat engine. Let me first of all tell you what are the 2 processes that take place in the Carnot cycle. The first process is the adiabatic process. What is actually happening in the adiabatic process? During this process, no heat flows in the system and no heat can flow outside the system. From the first law, this means that Q is equal to 0 and U is equal to minus W, minus of work done. The next process is that will define a Carnot cycle, or that is involved in the Carnot cycle, is the isothermal process. Now what is an isothermal process? Isothermal process is a process that is occurring at constant temperature. That is, during this process, when a system is going from state 1 to state 2, it does not have any change in temperature and no change in internal energy consequently also takes place. In this process, according to the first law, the internal energy U is equal to 0 and Q is equal to W, that is, the heat flowing is equal to the work done. This figure is showing the ideal gas piston model of the Carnot cycle. So as you can see, the Carnot cycle is a very, very simple apparatus. It just consists of a cylinder which is having the ideal gas in it, fitted with a piston. Of course, all the things are insulated. The piston is insulated, it is free from any conduction loss, convection loss, and it is totally frictionless movement of the piston. Now let me show you the Carnot cycle PV diagram. As you may be aware, every cycle can be represented on various diagrams, whether it is PV diagram, it is TS diagram, it is PT diagram. Most popular diagram is the PV diagram, and mostly the cycles are represented on the PV diagram. Now as mentioned just now, the Carnot cycle is made up of 4 reversible processes. Process 1 to 2. That denotes the reversible adiabatic compression. It means when the state system is going from ideal gas is going from state 1 to state 2, it does not undergo any changes in heat. Process 2 to 3 is the reversible isothermal expansion. Process 3 to 4 is the reversible adiabatic expansion. And process 4 to 1 is the reversible isothermal compression. Now as you can see, this whole cycle is operating in a cycle. That is, starting from 1, the ideal gas goes to state 2, state 3, state 4 and back to 1, because for a heat engine to operate, it has to operate in a cyclic manner. For a machine to be useful, it has to operate in a cyclic manner. The PV diagram of the cycle is shown in the figure. Now, one very important thing, we can calculate the work done by the gas from the PV diagram itself. We see that the area under the curve 1, 2, 3 is the work done by the gas during the expansion part of the cycle. The area under the curve 3, 4, 1 is the work done on the gas during the compression part of the cycle. The area enclosed by the path of the cycle, that is 1, 2, 3, 4, 1 area, is the difference between these two and represents the net work done during the cycle. This is what we will be calculating when we calculate the efficiency of the Carnot engine. Now let us concentrate and discuss each process in detail, because if we are to calculate the efficiency of the Carnot cycle, we must know two things: the work done, total work done, and the heat absorbed. To find out the total work done, we should have an idea of the work done along each process, that is from 1 to 2, 2 to 3, 3 to 4 and from 4 to 1. So let us concentrate first of all on the reversible isothermal expansion which is occurring from 1 to 2. The temperature T1 is a constant. The temperature of the gas is T1 and the cylinder is in close contact with source at temperature T1. The gas is allowed to expand slowly, doing work on the surroundings, and is positive by sign convention. It continues until the gas reaches state 2. The amount of total heat transferred to the gas during this process is Q1. It means that from state 1 to state 2, the ideal gas is absorbing heat Q1 from the source. Now let us consider the second process that is occurring, the reversible adiabatic expansion, that is from 2 to 3. At state 2, the reservoir that was in contact with the cylinder head is removed and the gas is thermally isolated. The gas undergoes reversible adiabatic expansion, doing work on the surroundings until its temperature drops from T1 to T2 and the gas reaches state 3. In this process, what is happening is this, that the internal energy of the system is decreasing, which is causing the pressure and temperature to decrease also. The work is done by the gas and is negative as per sign convention. Because this process is adiabatic in nature, no heat is being absorbed and no heat is being lost. Next, we come to process 3. Process 3 is the reversible isothermal compression. That is, process which is taking the ideal gas from state 3 to state 4, keeping the temperature constant, and now the temperature is T2, which is the temperature of the sink. At state 3, the cylinder is placed in thermal contact with the sink at temperature T2. Now the piston is pushed inwards by an external force doing work on the gas. As you can see, why is this very important, isothermal compression? Because we should have an engine that is operating in a cyclic manner. It means when we have come from 1 to 2 and 2 to 3, we have to come back to 1. To come back to 1, these two processes are very important, process 3 and process 4. As the gas is compressed, its temperature tends to rise. But as soon as it rises by a small amount dt, heat is transferred from the gas to the sink, causing the gas temperature to drop to T2, thus maintaining isothermal conditions. The amount of heat rejected from the gas during this process is Q2. Now again, the work is done by the gas, and by sign convention it is going to be negative. The process 4 now. Why is the process 4 important? Process 4 is important because it helps us in restoring state 1. And during this process, the work is done on the gas and is positive in nature. Process 4 is the reversible adiabatic compression. It allows the temperature of the gas to rise from T2 to T1. Gas is thermally isolated at state 4 and is compressed in a reversible manner such that the gas returns to its initial state, which is the state 1. During this process, the temperature rises from T2 to T1. The volume decreases while the pressure and temperature increases. So we have now seen what is happening in the 4 processes. Next step is to calculate the efficiency of the Carnot cycle. As discussed in earlier slide, eta is the ratio of the work done to the heat absorbed. To calculate eta of the Carnot cycle, we need to calculate the total work done in all the 4 processes as I had mentioned earlier. It means we have to calculate the work done from state 1 to state 2, state 2 to state 3, state 3 to state 4, and from state 4 to state 1, and then we have to add up all these works to get the total work done. So we will now calculate the total work done. First process, isothermal expansion. In this, the gas is going from state 1 to state 2. That is, the gas is taken from thermal coordinates P1, V1, T1 to P2, V2, T2, T1. Since the expansion is isothermal, the total change in internal energy is 0 and the heat absorbed by the gas is equal to the work done by the gas. So we calculate the work done. W1 going to 2 will be equal to Q1 will be equal to nRT1 log of V2 by V1. R is the gas constant, N is the number of moles, T1 is the temperature of the source. Next we will calculate the work done when the gas is undergoing adiabatic expansion. It means going from state 2 to state 3. The gas expands adiabatically from P2 V2 T1 to P3 V3 T2. Here the work is done by the gas and is given by W2 to 3 equal to nR over gamma minus 1 T1 minus T2. N is the number of moles, R is the gas constant, T1 is the temperature of the source and T2 is the temperature of the sink. Gamma is Cp by Cv. The next process is the isothermal compression, which is taking the gas from state 3 to state 4. The gas is compressed isothermally from the state P3 V3 T2 to P4 V4 T2. As you can see, temperature is T2 only because this is isothermal compression. Here the work is done on the gas by the environment and is given by W3 to 4 nRT2 log V4 by V3, which is equal to Q2. The next process is the adiabatic compression. The gas is compressed adiabatically from the state P4 V4 T2 to P1 V1 T1. Now as you can see, the temperature is rising from T2 to T1 during this process. Here the work is done on the gas by the surroundings and is given by W4 to 1 is equal to nR over gamma minus 1 T2 minus T1, which is equal to minus W2 to 3. It means the work done by the gas in going from state 4 to 1 is the negative of the work done by the gas from going from 2 to 3. So we have calculated individual work done during the 4 processes. To calculate the total work done now, we have to add up all the 4 work dones. Therefore, the total work done by the gas on the environment in one complete cycle is given by this: W1 to 2 plus W2 to 3 plus W3 to 4 plus W4 to 1. By substituting the values of W's calculated in the earlier slides, we will get W equal to nR T1 log of V2 by V1 plus nR T2 log V4 by V3. Now this requires further simplification to get the efficiency of the Carnot cycle in a simpler and more usable formula. So reiterating what we have discussed earlier, eta is the ratio of the net work done by the gas to the heat absorbed by the gas. That is, it is equal to W by Q1. Substituting the values of work done in the formula and substituting the value of heat absorbed in the formula, we get eta is equal to nR T1 log of V2 by V1 plus nR T2 log of V4 by V3 divided by nR T1 log of V2 by V1. Here V1 is the volume of the gas at state 1, V2 is the volume of the gas at state 2, V3 is the volume of the gas at state 3, and V4 is the volume of the gas at state 4. R is the gas constant and N is the number of moles. T1 is the temperature of the source and T2 is the temperature of the sink. Since the step 2 to 3 is an adiabatic process, we can further write it as T1 V2 gamma minus 1 is equal to T2 V3 gamma minus 1. Simplifying this further, we get V2 by V3 is equal to T2 by T1 raised to the power 1 by gamma minus 1. Similarly, for the process 4 to 1, we can write V1 by V2 equal to T2 by T1 raised to the power 1 by gamma minus 1. Thus, V2 by V3 can be written as V1 by V2. So, the expression for net efficiency of the Carnot engine is reducing to the well-known formula eta is equal to 1 minus T2 by T1. Here T2 is the temperature of the sink and T1 is the temperature of the source. So you can see the factors on which the efficiency of a Carnot cycle depends. It depends upon the temperature of source and temperature of sink. It is always less than unity. If T2 is equal to 0, eta is 1. That is 100% efficiency. But it is not possible because absolute 0 is unattainable. So 100% conversion of heat into work is not possible. The search continues. Efficiency is minimum or 0 when T1 is equal to T2. Temperature will not work. Engine will not work. Why? Because engine needs 2 different temperatures, 2 different reservoirs to work. To increase eta, either T2 has to decrease or T1 has to increase. But decrease in T2 will be more effective. So we have discussed in detail the most important cycle in thermal physics, which is the Carnot cycle. And as you can see, it is the ultimate aim to have into effect a heat engine whose efficiency is large and heat losses is less. But that search is still continuing. Carnot engine, I will reiterate, is an ideal engine. It cannot be realized in practice, but every engine, every other engine is compared to a Carnot engine to evaluate how efficient the other engine is. So again, I can show you the PV diagram so that you have a clear idea about what is happening here. P2 from state 1 to state 2, we have isothermal expansion. From state 2 to 3, we have adiabatic expansion. From state 3 to 4, we have isothermal compression, and from state 4 to 1, we have adiabatic compression. So I hope students you have understood the Carnot cycle, and we will move on. I will also discuss more cycles with you in this lecture series. The next cycle is the Stirling cycle. So any cycle and the heat engine that follows this cycle will be called the Stirling engine. This is the PV diagram of the Stirling cycle. As you can again see, it has 4 processes. It is invented by Robert Stirling. You can see the state is going from, the processes are 4, going from 1 to 2, 2 to 3, 3 to 4, 4 to 1, and the cycle is represented again on the PV diagram. You have 2 isocores, as you can see. This cycle is taking place between 2 isotherms and 2 isocores. It means 2 processes are occurring at constant temperatures and 2 processes are occurring at constant volume. Now please remember that wherever the process is occurring at constant volume, the work done is going to be 0, and wherever the process is taking place between constant temperatures, the process is isothermal in nature and heat is going to be absorbed and rejected. Note that provided the working substance is an ideal gas, there is no change in the internal energy along the isotherms. The work done by or on the gas is equal to the heat gained by or lost from it. No work is done along the isocores.